Welcome. I'm truly excited to be here today to talk to you guys about location and sensors. Get the clicker. My name's Steve Malkos. I'm the technical program manager for the Android location and context team. I was amazed earlier today to hear Sundar talk so much on sensors and context. Being part of the location and context team, we touch every part of Google, and I'm truly excited about that. So, without further ado, okay, let's get into it. Today, we carry the world in our pocket. We carry more computing power at faster data speeds than we did just nearly half a decade ago from our desktop PCs. One item that has remained the same throughout our computing history has been building these innovative software applications, and you guys are continuously shaping this world. But we need to do more. We can do more. We could build deeper and richer experiences. In this talk, we'll focus on what it takes to build an awareness application. We'll go through sensors and location, focusing on bringing richer experiences by using them. Then we'll take a deep dive into the Android Sensor Hub and go through the cool new things that we're building for it. Awesome. Okay, so what does it take to build these highly contextual apps? So what does it take to build these high-quality apps? Today, sorry, the notes are not right.
Let me take care of that for you.
Our phones are very personal and interactive. They have transformed the way we compose our day. We use them to get traffic info, health and safety, and notifications, and much more. So it's understandable that your biggest concerns are on how to make your apps more contextually aware. So let's focus on what it takes to build these high-quality apps. When creating these awareness applications, there are typically three main layers that we need to look at. That's sensors, algorithms, and user experiences. Think of an awareness application like a human sense. For example, your inner ear acts as the accelerometer and gyroscope of the device. Your eyes act as the camera sensor. That raw data from your ears to your eyes gets sent up to your brain and processed like the algorithms on the device. That's then classified into the context and outputs as the user experience, like I'm running, or I'm running with a buddy. MEMS sensors allows us to take a deeper programming perspective on comprehending the environment around us. So when building these contextual applications, we're going to focus on these four main pillars. That's coverage, accuracy, latency, and power. We'll refer to these pillars throughout the entire talk. These are the building blocks for creating higher quality applications. Let's walk through examples of each of these. The first pillar is coverage. For location, it must work all the time, indoors, outdoors, and in every country. At Google, we're continuing to improve our coverage maps with our crowdsourced models and Google databases to make location better. For activity recognition, it has to support a wide array of different types of activities, like I'm running, or I'm walking, or I'm in a vehicle. And nearby notifications needs to work across a wide array of different types of devices. Finally, sensors have to work seamlessly and uniformly across the entire ecosystem. The second pillar, accuracy. From the macro view, GPS must be very accurate. Users don't want position jumps. They want the positions to be under 5 meters all the time. Indoor and outdoor transitions also have to be as smooth as possible. From the macro view that we saw on the previous column to the micro view on position accuracies, it must work perfectly for our virtual world. Examples of better virtual reality can come from sensors. Sensors that output less drift at lower noise. A user also wants very accurate activity detection. For example, it's not okay to classify biking activity if you're shaking your leg in a moving car. The third column that I'd like to discuss is latency. From the macro view, Users don't want to wait for their positions. Location should show up instantaneously. And activity detection needs to happen near real time so the user's entire activity can be tracked with almost no latency. From the macro to the micro on latencies, our sensors cannot lag. When we have sensor and display lags like this, your virtual world can go from making you a beautiful scene to making you nauseated very quickly. We want the experience to be crystal clear. We take great care in ensuring that our sensor latency requirements are met. This ensures that when you write your applications, you could be certain that they'll perform to your users' expectations. Our final column, power. That's battery life, one of the most important columns when building your applications. We all know that if your application sucks up the user's battery life, they'll quickly uninstall it from their device. We need to make it where you guys don't have to worry about power. We can do this by avoiding too many knobs. Simplicity is key. Power has even two sub-pillars. That's latency and accuracy. It means we could run more often, improving on latencies. It also means we could get access to more signals, thus improving on accuracy. So in the theme of building better user experiences by bringing higher quality applications focused on coverage, accuracy, latency, and power, let's hear from Ashutosh on Android sensors.
Thanks. Hi. Thanks, Steve, for setting out the lay of the land for the rest of the presentation. I'm Ashutosh, and over the next few minutes, we shall be talking about how we set about achieving these 4 pillars of context for sensors. I hope to give you some insight into the challenges we face and the power we derived in working with the ecosystem. I shall show you some of the new and shiny things we have in store for you for Android N. And finally, we'll share some of the lessons that we've learned in developing Android experiences, which will probably be of value to you as well. A challenge that we face is the constant tension between increasing coverage by formally defining new sensors in Android and ensuring that we can keep a consistent user experience across the ecosystem. Let me give you an example. We have received requests to allow accelerometers that only support 2 axes. These are required for low-end markets where the z-axis is not required if the only thing that accelerometer does is detect landscape and portrait detection. On the other hand, we have been asked to mandate a higher dynamic range for accelerometers because it allows some safety applications to be developed which can potentially save lives. The problem is that these 2 goals are mutually contradictory. A sensor that only supports 2 axes will not have a high dynamic range. The economics of the industry work against it. The example goes to coverage. We must ensure that all Android sensors can eke out the maximum visibility from the hardware, while also ensuring that the application developers see consistent APIs across all of Android. Over the years, we've steadily added new formal sensor definitions. While the major physical sensors like Accel, Gyro, and MAG were defined very early on, we've continued to define new capabilities like sensor fusion, rotation vector, geomagnetic rotation vector, and new sensor types for completely new form factors like Android Wear. These new capabilities increase coverage to develop awareness applications because more sensor types mean that we can get more data about the world around us and derive richer inferences. We are adding a few things this year for the Android N release. Let me walk you through some of them. Let's start with something really exciting. All orientation sensors thus far were centered around orientation. They provided the orientation of the device in terms of roll, pitch, and yaw, with reference to either true north or gravity or an arbitrary initial point. We are adding the 3 axes of translational freedom by introducing the 6 DOF sensor type. Apps will not only know the orientation, but the precise displacement of the device in the world. This means that motion control in games can go just beyond tracking where the user is looking. Now they will be able to move the player in the virtual world just as the player moves in the real world. You can walk and not just spin in place. Augmented reality experiences will be even more immersive now that they can mirror the user's movements. Just to set expectations, this sensor is not likely to be widely pervasive across Android, but we believe that the introduction of a formal sensor type is required to give the system a push towards augmented reality applications. On the wearables form factor, we're extending the capabilities of what is available through the heart rate sensor. Thus far, you have been able to get an average snapshot of the heartbeat measurement, which is great, but it leaves a lot of information on the table. We will expose a much more finer-grained event for every heartbeat, which should more or less correspond to the systolic peak for each heartbeat. This will enable a whole new class of fitness and wellness applications, like reporting and monitoring mental stress, physical stress, overtraining, exercise recovery, and sleep analysis, etc. And you guys will be writing all of them. One of the most oft-repeated requests from app developers to us was to expose the hardware capabilities to determine the motion state of the device. We are adding these sensors to the Android Sensors API as one-shot events. We shall expose two of them. One shall fire if the device enters a stationary state, and one that fires if the device starts moving. We hope that this will allow the applications to be more judicious in the use of system resources, and developers will use this ability of motion determination in low-power hardware to gate their resource usage. Finally, this year we realized that application processors and display controllers are now smart enough to enter low-power states. If only we did not keep pinging the application processor with accelerometer data to compute the device orientation. So we're formalizing the screen orientation as a new sensor type that can be implemented by the OEMs to get their low-power domains to compute the device orientation. However, developers can and should continue to use the Android Activity and Window Manager APIs. Android will ensure that regardless of the underlying sensor support, your app will continue to work seamlessly across all addressable devices, and if this sensor is supported, you get all the power benefits. Finally, we are adding capabilities to allow applications on an Android device to discover and subscribe to external sensors through the Sensors API. By external sensors here, I mean any sensor that is not present on the device when the device boots up. Now, this can be an accessory for the device that physically attaches to the device, or a truly external device that connects wirelessly to your phone. This is a nod to the central roles that our phone have in our lives, and the realization that a single device cannot be all things to all of the people all of the time. Device capabilities can be augmented, and we want to provide a standard way to access such data. What is coming up is exciting, and I cannot wait to see what cool things the developers will come up with these new sensor types. Having decided how we want to increase coverage, how do we establish accuracy and consistency? How do we ensure that when a new API version is released, what makes it to the app developers is consistent across Android? This is a complex process and involves the hard work of hundreds of talented people across the Android ecosystem. Let me walk you through some of the challenges. Android is diverse. Just on the hardware side, there are 300 plus OEMs, 200 plus carriers and operators, hundreds of component vendors, and dozens of CPU SoC vendors with a range of products. There are dominant players that have huge market shares, and there's a long tail that caters to very specific niche cases. Somehow, we have to ensure that we're listening to everyone and helping everyone in the ecosystem succeed. And then there's the sheer range of devices that Android can support. All of the devices on this slide are Android devices. The same specifications rule them all, more or less. There are few restrictions or mandates that Android stipulates. As an example, it's completely OK to make an Android device without a single sensor type, not even an accelerometer. That sounds bizarre if one thinks of Android purely as a cell phone platform. But it's immediately obvious once you think of Android TV products and convince yourself that determining the device orientation of a TV would be an edge case at best. So, what does it really mean to support a sensor? What sensors should a device have? What guarantees, if many, are made explicit to the developer, and how? These are difficult questions that keep us busy. And once there's agreement on these goals, how does this diverse ecosystem take its cues? What tools do we use to make this happen? In a nutshell, we drive this process by creating standards for Android, producing exemplary Android devices at Google, and working in tight collaboration with our partners. The very first step is the definition of Android compatibility. An Android device is supposed to meet 100% of the specifications as defined in the Android compatibility document, the Android CDD. It goes into lots of gory details about what kind of sensors should be on a device, how they should be announced, and if announced, what bars they must meet. We tune the CDD language to advise the ecosystem on what is coming down the road and nudge them into more aspirational requirements. The CDD is enforced through the CTS, a compatibility test suite. All Android devices must pass the CTS. There are no exceptions or any waivers for any device. We keep adding CTS tests to patch holes in our testing. Note, however, that the CTS is an enforcement mechanism only. It cannot possibly cover the entire specifications exhaustively. The artifact of record is the CDD. What do we expect of developers? Please take a look at the Android CDD if you're looking to deploy an app across a large user base. It will help set your expectations on what is standardized and what to expect. Google devices are another tool we use. All Google devices are great devices. They also serve to set a bar for the rest of the OEMs. A Nexus device is subject to a lot of scrutiny outside Google. The OEMs scrutinize it to make sure that their devices in that class are as good as or even better than the Nexus. They also use that opportunity to figure out the holes in our specifications. If something is ambiguous, a reasonably good assumption would be to go along with what the Nexus is doing. The implication here is obvious. Do test your applications on Google devices. I think most of you follow this practice already, but please, however, go beyond just the Nexus that launches this year. Do test your applications on previous Nexus devices and extend your testing to, say, Android One devices. On the sensor side, we go even further. Last year, Google wrote the sensor stack completely by itself, and we are releasing the complete sensor stack source for the Nexus devices in open source. You can get the code for the Sensors Hub software at the repository on this slide. We have two primary reasons to do this. The first is to make life easier for the ecosystem. They now have access to the source code that runs on the Nexus devices and should be able to comply with all the requirements we are putting forth, and hopefully even do better. The second is guidance. We hope that simply by releasing the source code, we convey our intents and expectations very loudly. In fact, if you look at the source code released, you will find the beginnings and the genesis of some of the future work that we shall release in Android N. We have not written a ton of formal documentation yet, but we are finding that our partners are reading the release source and coming up with a very good idea about what to expect. Finally, we must continue to build internal expertise to keep abreast of the developments in this space. We learn constantly and continue to invest in internal capabilities to learn more about sensors and algorithms. Let me show you how here at Google we're innovating new groundbreaking methods to test our solutions and improve the quality of our sensor algorithms. Can you play the video, please? In this video, you'll see Matt programming one of our robotic arms to simulate arm swinging for pedestrian dead reckoning solutions. In this example, you'll see two things happening. First, Matt will start by using a motion capture system. The motion capture system is able to record Matt's arm swings with centimeter-level precision. We then translate the exact motion of that capture system into a robotic arm. The robotic arm then repetitively tests that specific scenario on an automated basis again and again. That gives us the ground truth for us to test our algorithms and sensor solutions. Let's watch. That was cool, and Matt seemed to be having way too much fun on there. The final tool in our chest is collaboration with our partners. We work very closely with our partners throughout the year to make sure that they are aware of what we are doing. This is a symbiotic relationship. The partners want to make sure that their product roadmaps are aligned with ours, so they're not caught by surprise by any of the announcements we make. We, on the other hand, want to make sure that we are not shouting into thin air and have realistic expectations about what is achievable. We meet them constantly throughout the year. Every year, we hold an Android boot camp and give them a glimpse of our plans. On the sensors side, last year, we conducted mini summits with sensor vendors, SoC vendors, and the OEMs. If we are successful, nothing that I'm saying today would be a surprise to any of our partners. They should be sitting back and saying, we've got this taken care of. Here's the cool thing for you. Why do you think they listen to us? Other than our charming personalities, the reason they do is because they want to reach you, the developers. Some of the best and the brightest on this planet are developing incredibly exciting technologies, and they want them to be exposed to you. We are merely facilitating this meeting of immensely creative and smart people from both worlds. The ecosystem is what we derive our influence from. The ecosystem is what we serve. Takeaway: reach out to us. Let us know what you're looking for. What is missing? What needs improvement? What is truly exceptional and you want more of? You'll find plenty of ways to reach us at the end of the presentation. The Android Sensors API has not only become richer by adding more sensor types, it also gives great control for the developers to optimize system performance. In the next few minutes, I would like to talk about some recommendations that will make your apps scale across different tiers of devices and should, under the hood, optimize for the hardware that your app is using. I will use power as an example. As to the extent possible, you want to spend as little power for your apps. Let us look at some ways that will help you achieve this. On many devices, there's a multi-layer approach to processing, at least as far as sensors are concerned. At the very source, there are sensors like the accelerometers and the gyroscopes. Sensors today have come a long way from years ago and themselves consume very little power. They're really power efficient. Accelerometers and gyros today take less than a milliwatt to sample data. They embed smart algorithms like gestures and motion detection. Some even have rudimentary programming frameworks for customization. Then there's the application processor. This is your big honking chip that you're using when you're running apps or playing games. Running the application processor takes a substantial amount of power. So if every time you try to process a single measurement, you wake up the application processor, it becomes limiting very quickly. All the power savings from the sensors are dwarfed if the application processor wakes up too often. It consumes a lot of power and is incredibly powerful computation, but is also very power hungry. It has to stay on for a few seconds, even if it needs to do a little bit of processing. It needs time to wake up and sleep. If every time you get a sensor measurement, you wake up the application processor, it never gets a chance to go to sleep. So getting the application processor to sleep is a key power savings technique. Modern hardware adds an additional layer for sensor processing. We show that as a sensor hub in this diagram. This low power compute domain may be part of the sensor itself, a special power domain on the SoC, or a discrete chip. Its goal, however, is the same: to offload computation from the application processor and save power. There are a few hooks on the sensor's API that let you achieve this goal. For example, batching. You can use the sensor's API to specify the maximum delay your application can tolerate to receive sensor data. This means less frequent updates to the application processor. The events can be grouped and processed together. The bigger the storage buffers on the hubs, the more power is saved. Another design pattern is to specify the goal that you want to achieve and then be woken up when that situation becomes true. Then the low power hardware can monitor for the decision to become true instead of the main application processor. This allows always on monitoring of events that would have been prohibitive by looking at the raw sensor data all the time. And as an example, if you wanted to change the app behavior when it looks like the user has moved from one place to another, you can use a combination of geofences and the significant motion sensor type to gate your processing. For the end release, we have added new sensor types to detect motion and stationarity. By using the right triggers, you will consume power only when needed and not miss a moment of interest for you. A less obvious design pattern is to use the highest level of abstraction possible. While the APIs may look like they're all exposed at one level, if you become a little familiar with how the system is built, you will be able to see where in the system the APIs are tapping into. Take, for example, the sensors, accelerometers, gyros, and magnetometers. If you access the raw data, the system must ensure of its end of the contract and give you accurate, reliable, and timely data. It cannot and should not put in any smarts. However, if you ask for the rotation vector, the same sensors are used and data is fused. It may be tempting to roll your own sensor fusion algorithm by processing the raw data directly. However, you will lose hardware optimizations on the table. As an example, most devices today, if they're computing the rotation vector in hardware, sample the underlying sensors at an extremely high rate, sometimes in the order of kilohertz. There is no way we can support that frequency of updates on the application processor. And if by rolling your own sensor fusion algorithms, you would be leaving power and performance on the table. So this is pretty complex, I hear you. We have been trying to come up with a specification that lets the application developers know that the sensors on a device are top-notch. In the MNC release, we added exactly such a signal for the developers. We call it Hi-Fi sensors. If the feature is defined, you will know that the sensors are really accurate. There are stringent requirements on the resolution, range, and performance of all the expected sensors. You will know that a large batch size is supported, allowing you to conserve battery. You will know that the timestamps on the sensors will be very highly accurate. For many applications that integrate sensor values over time, for example, dead reckoning, an error in the timestamps is the same as an error in the sensor value itself, and often worse. Finally, you will know that sensors are low latency. Hi-Fi sensors have stringent latency requirements to support all possible real-time interactive use cases that we have run into. Checking for the Hi-Fi sensor support is very easy. This code snippet shows you how to do it. We're simply looking for a feature string to be declared. So with a quick query to the package manager, you can be assured that your device has great sensors and will support all the fundamental pillars of contextual awareness. Sensor capabilities are improving, getting more ubiquitous, and we are seeing a huge demand for these additional capabilities. We are the location and context team. We're constantly working on integrating sensors into everyday user experiences to make our Android devices useful and a delight to use. Location is the other huge and complex sensor that our services consume. I will hand it over to David to walk you through that part of the story.
Thanks, Ashutosh. Hi, I'm David, and I work as a software engineer on the Android location team. You've just heard about a lot of the exciting capabilities we have with low-level sensors, and now I'm going to talk about our higher-level location APIs and how they do a lot of the sensor fusion work for you. The Fuse Location Provider is our primary API for producing locations. It combines many of the sensors Ashutosh just talked about, including GPS, Wi-Fi, cell, accelerometer, magnetometer, and gyroscope. It's used by Google Maps to power the current location blue dot, and by Google Now to provide invisible assistance like reminding you where you parked your car. Android apps provide input hints on accuracy requirements and frequency, and the FLP decides which sensors to turn on in order to manage both power and accuracy within the constraints of user settings. In the next few slides, I'll dive into the details of some of these sensors and show how the FLP uses them. GPS is one of the most mature location sensors that we use, and when it works, it usually works great. It shines outdoors when you have a clear view of the sky, but it has some trouble in cities with tall buildings, and when you're indoors, it often doesn't work at all. It's relatively power hungry, and it eats the battery pretty quickly when active. The FLP will use GPS when an app requests the highest accuracy location available. It will also sometimes use GPS for balanced power app requests on newer devices that support GPS batching. Wi-Fi is another staple location technology that has become more and more useful as Wi-Fi access points have proliferated around the world. Unlike GPS, it works well indoors where people typically have Wi-Fi. The accuracy usually isn't as good as GPS, but it's good enough to tell you what part of the building you're in and often what floor you're on. Like GPS, the power isn't great, but it can be improved by reducing the location frequency. And knowing which cell tower you're connected to also gives a very coarse estimate of location. It can usually tell you which city you're in and sometimes which neighborhood. Unlike GPS and Wi-Fi, it works both indoors and out. And the battery life is great, given that the cell modem is continually reconnecting to cell towers anyway. So GPS, Wi-Fi, and cell are the foundation of location sensors surfaced through the FLP. But one of the best parts of using the FLP in your applications is that you continually take advantage of new Google developments in both hardware adoption and algorithm improvements. Most of these improvements become active in your apps without any code changes. In the next few slides, I'll highlight some of the improvements we've recently made and show how to take advantage of them in your apps. As I mentioned before, dense urban environments are very challenging for GPS. When driving near tall buildings, it's common for the location to drift or jump to the wrong block. At Google, we test GPS on a variety of phones and environments. This image shows a setup for driving tests that we perform in San Francisco, which is one of the harshest GPS environments on the West Coast. We use a military-grade inertial navigation system that provides centimeter-level accuracy in order to collect ground truth location for comparison. We also take video imagery to compare position jumps and lags when all devices are in navigation mode. This gives us the automated ability to count and measure each device's position jump or lag, and then produce a report listing the exact moment when a device experienced these lags and jumps. This is an example test drive in downtown San Francisco. You can see a lot of issues with this track. Positions clumped together, poor latency, and even some positions inside buildings. In order to solve some of these problems, we've worked with our GPS chipset partners to incorporate their sensor fusion algorithms that combine accelerometer, gyroscope, magnetometer, and barometer with raw GPS pseudo-ranges. The chipset can fall back to these other sensors when the GPS signal is weak, providing a much better user experience. This image shows a before and after result of this GPS chipset fusion working on a Nexus 6P. You can see the blue line provides a much more stable position resulting from this fusion as the user drives in an urban environment. We've also tackled accuracy in our Wi-Fi location models. Over the last year, we've improved indoor median accuracy by 40%. In Google Maps, this can mean the difference between knowing that you're in a shopping mall and knowing how close you are to the actual store you're trying to find. We've added significant use of the inertial sensors, accelerometer, gyroscope, and magnetometer. These sensors don't tell us where the user is directly, but they describe how the user moves, so we can use them in conjunction with GPS and Wi-Fi to improve location. One example of how the FLP uses the accelerometer is by activating it when the device is stationary in order to save power. Rather than performing costly Wi-Fi scans over and over again, we rely on the low-power accelerometer to tell us when the device moves, at which point we resume Wi-Fi scanning. We also use all three of these sensors to improve the accuracy of Wi-Fi location. If you open Google Maps indoors and walk around, you may notice the blue dot follow you around the building. As I mentioned before, Wi-Fi accuracy alone is not that great, but by using sensors, we can count your steps, detect when you turn, and combine this information with Wi-Fi to hone in on a more accurate location. Now, Ashutosh already talked about sensor batching, where we can accumulate sensor data on low-power hardware and process it later. Likewise, we've added support in the FLP for location batching, where it collects location data at lower power and processes a batch of locations after the fact. If your application doesn't need immediate location updates, you can save significant battery by requesting batching. This allows the FLP to utilize sensor batching under the hood and also to consolidate network queries. An example of this use case might be a fitness app that tracks the user's activity. The user will periodically want to check their progress throughout the day, but doesn't necessarily need constant updates. Unlike the other FLP improvements I've mentioned, location batching requires code changes in order to activate the power savings in your app. Here's a code example to activate batching. You use a location request object to provide your app's constraints to the FLP. The setInterval method tells the FLP how frequently to compute locations. To activate batching, the magic wait call is setMaxWaitTime, which tells the FLP how frequently to deliver locations to your app. So in this particular example, the FLP will compute a location every minute, but will deliver them to the app every 5 minutes, typically in batches of 5 locations. Now, back to the fitness app example. Let's say it's batching the user's locations, and then the user opens the app and wants to see their progress immediately. The app can call flush locations, which tells the FLP to interrupt the batch in progress and deliver the most up-to-date locations as soon as possible. The user will see all locations collected in the app, and then batching will continue as previously requested. So by making a few code modifications, the fitness app can take advantage of location batching with significant power savings while still providing the same responsive user experience. Now that we've seen the latest features of the Fuse location provider, I want to briefly overview another set of location APIs, geofencing. The geofencing APIs notify your app when the user enters or exits predefined areas of interest, such as their work or home. It's built on top of the FLP, so it inherits all the new features we just talked about that improve accuracy and conserve power. In addition, geofencing uses activity recognition to dynamically manage power based on the user's speed and proximity to the geofences of interest. This code sample shows how to incorporate geofencing into your apps. You define up to 100 circular regions of interest and register for notification. I've highlighted the set notification responsiveness call because it's very important for minimizing power consumption. It specifies the delay you can tolerate in receiving notification when the user enters or exits a geofence. So your app should set this to be as high as is reasonable for your use case. So I've shown a brief overview of our location APIs and how they do the work of fusing the latest and greatest sensor technologies for you. Now I'll hand it back to Steve, who's going to talk about our upcoming hardware features and how we plan to incorporate them into our APIs.
Great. Awesome. Thanks, David. We just heard how we're moving more and more algorithms down into our low-power processing domains, or how we just want to offload as much as we can from the main application processor. Next, I'm going to take a deep dive and talk to you about the Android Sensor Hub and the cool new things that we're building for it. Okay, our mission with the Android Sensor Hub is to use all sensors and all wireless radios on a mobile device so we can have a better understanding of the state of the user's context and location. We want to simplify our users' interactions. For example, pick up to wake the device. We want to augment human memory and knowledge, like we did with Google Now with Where's My Car? And we want the users to have a better understanding of themselves, like Google Fit. So what did we launch? In Marshmallow, we launched a standalone microcontroller which runs always-on processing. We did this on the Nexus 5X and 6P, and we open-sourced it to the ecosystem. Why did we need this separate processor? Today, the cost of computing activities in an always-on fashion for location and activity recognition is really cost prohibitive because of power. By introducing this tiny 3x3 millimeter chip, we could reduce latencies, improve accuracies without hardly affecting the user's battery life. I'd like to highlight, though, that sensor hubs are not anything new. They've been around for many years. However, at Google, we wanted to standardize on this output so that there's more consistency in the ecosystem. This gives us better assurances that when you write your applications, they'll work the same across all Android. So what did we do? How did we do this? We connected the following into the Android Sensor Hub: accelerometer, gyroscope, magnetometer, barometer, proximity, and ambient light sensor. By establishing these connections, we were able to achieve the following. I'm not going to read through this whole list, but I want to highlight some examples. It's running everything in sensors.h. This includes things like game rotation vectors, gravity. We're running significant motion detector, which is the primary use case for Android doze mode. All of our activity recognition models are in this hub. And we introduced new gestures like double twist, which is a private sensor that you could register your application to today. So what are we saving in terms of power? It's quite simple. When you run activity recognition on the application processor, it consumes quite a bit of power. When we introduced sensor batching, we were able to cut that number down in half. Running that same activity recognition model on the Android Sensor Hub costs us just a fraction of the power. And this is just the start. So here's a sneak peek on what we're working on this year. I'm going to highlight some of the big items. We're introducing GPS pseudo-ranges. This is groundbreaking, as it's the first time in history a mobile application will have direct access to the raw GPS measurements. This is beneficial to many, but especially the phone makers, because they could use these measurements to help them in their GPS performance testing. And if you ever had a bright idea on how to use GPS measurements, now's your time to shine. We're also introducing personalized activity recognition models, because we all know my step length's different from your step length. By having a personalized model, we'll be able to better our accuracies for activity recognition. With the Android Sensor Hub, we'll introduce downloadable code. In Marshmallow, when we launched activity recognition, we lost the capability of updating our algorithms frequently, but gained the power savings by running those in the low power domain. In Nexus N, or Android N, we'll have the best of both worlds. Low power activity recognition with the capabilities of continually updating our algorithms. We'll also connect GPS, Wi-Fi, and cell directly into the Sensor Hub, which I'll talk about in the next slide. So by adding these additional connectivity signals, we're going to move our entire location engine into the hub. I noted earlier that power has two sub-pillars. Those were latency and accuracy. By moving the location stack down into the low power domain, we'll improve geofencing because the location engine's running there. So latency will become better because we could run more often, and accuracies will become better because we will have access to more signals. So those are the main themes for this year. Let's touch a bit in the future. In order to truly understand the state of a user's context and location, we need to answer the following three key questions. Where's the user? Examples: GPS, latitude, longitude. Geofencing, which is within your circle or not. And semantic location, like where am I? I'm in Starbucks. For activity, we need to answer what is the user doing? Are they walking, running, on a bike? And for nearby, we need to answer, which devices can I connect to? Which Chromecast devices are nearby? So in order to achieve or answer these three key questions, we need to push down everything listed here into the low power compute domain. For location, we're already working on the Fuse location provider and geofencing this year. For activity recognition, we'll continue to add new sensors and new activity recognition algorithms down into the low power domain. And for nearby, we'll work on adding nearby connections and messages into the low power domain. So by answering these three key questions, the Android Sensor Hub will bring the best of Google's databases, machine learning algorithms, and Google infrastructure at the lowest power. This will allow us to bring you always-on location and personalized context. We'll continue to add more and more signals down into these low-power domains. We've already achieved activity recognition and sensors in Marshmallow, and soon are about to launch location and dynamically downloadable code in N. The future will become more and more contextually aware, and by adding these signals, will help make you deeper, richer experiences in your applications. We're truly excited about these possibilities and are looking forward to ushering a new wave of APIs for your applications. Thank you. So I have one last slide, if we could go. We have a new developer site. This is a nice refresh site. Go to developers.google.com/location-awareness. We've placed all of our APIs in a fresh new look for you guys to access our location and context information. We also have a quick survey that we'd be really interested in getting your feedback on our sensor APIs. So please go to the second link and fill out this quick and easy survey. You could do it at your leisure or do it right now. And then lastly, David, Ashutosh, and I will hang outside for a little while if you guys have any questions, or we have office hours on Thursday and Friday at these times. Thank you very much.